Degrees of freedom is a concept that you'll find cropping up repeatedly in statistics you have to do for your degree. For example, you'll usually have to quote a value for the degrees of freedom when you present the results of statistical tests. Also, calculating certain kinds of estimates, like the standard deviation of a sample, involves degrees of freedom. But calculating others, like the mean, doesn't. Why? And is this the same degrees of freedom concept as the ones you quote alongside a statistical test? Well, the first thing to say is, understanding actually what degrees of freedom mean isn't desperately important for this module. You'll need to write the degrees of freedom down in your assessment, but you don't need to understand exactly what it is. Degrees of freedom is a tricky concept. Many good biologists can't tell you exactly what it is. This video is just for context, so that you have a chance to understand this number that you're being asked to write down for your assessment. I'll give you its definition first, but this won't mean much until I start to give you some examples. Whenever you calculate something, anything like a mean, standard deviation or test statistic, the degrees of freedom is how many independent pieces of information you needed in order to make that calculation. Now that sounds like I'm talking about the sample size, but it's not the same as your sample size, as we're about to see. The degrees of freedom are going to be different depending on what particular calculation it is you're making. And, here's the really important bit, they will also be different depending on what you already have to know before you make the calculation. The simplest example of degrees of freedom is a coin toss. A coin toss has 1 degree of freedom. If you toss a coin, you know you can only get heads or tails, so you know in advance of tossing the coin that the total number of possible outcomes is 2. If you get heads, you automatically know that you haven't got tails. I don't have to ask you, but did you also get tails? Given that we already know there are 2 possible outcomes, then one piece of information, whether we got heads, allows us to work out also whether we got tails. This is a system with 1 degree of freedom. Now let's say I while away some time by tossing a coin 100 times. You want to know how many heads and tails I got. What you know in advance here is how many times I tossed the coin, and also that there are only 2 possible outcomes. Again, only one piece of information is now needed to work everything out. If you know the number of heads I got, you automatically know the number of tails I got. So you only need to ask me one thing. So even though we have 100 coin tosses, given that we also know that there are only 2 outcomes, we still have only 1 degree of freedom, because only one piece of information is needed to work out everything we want to know. In contrast, here is a system with 2 degrees of freedom. You and I are having a phone conversation, and you tell me that you're looking at a traffic light. I ask you over the phone, what colour is the light? Now I know in advance that there are 3 possible outcomes, red, amber or green. Or you tell me, well, it isn't amber. Now that leaves me with 2 choices, so I still don't know what colour it is. So I say, stop toying with me, what colour is it? And you tell me, well, it's not green either. And now I know the light must be red. Given that we know there were 3 possible outcomes, 2 pieces of information were needed to work out everything we needed to know. This is a system with 2 degrees of freedom. Another case with 2 degrees of freedom is the 3 cup and ball trick. You're trying to work out where the ball is. You know in advance that the ball can only be in one of 3 cups. You turn over the yellow one and it isn't in there, but you still don't know where the ball is. You turn over the red one and it's not there either. Now you don't have to turn over the blue cup. It must be in there because it wasn't in the other 2. 3 possible outcomes, 2 required pieces of information, 2 degrees of freedom. So those examples are all for cases where the data are categories, like red, green, heads or tails. In these cases, the degrees of freedom is usually the number of categories minus 1. Now, let's widen our imagination a bit and see how this applies to things we can measure. When you calculate the mean of a sample, you don't know anything beforehand. and the value of the mean that you get will depend on each and every one of the values in your sample. In other words, if any one of those values varies, even slightly, you'll get a different value from your mean. But, as we're about to see, this isn't the case for standard deviation. As we learnt in our lecture, calculating standard deviation involves subtracting the mean from each value. So, in order to calculate the standard deviation, you first have to know the mean. Otherwise, you can't work out how much each value deviates from that mean. Without first knowing the mean, standard deviation doesn't make sense. This is a bit like knowing the number of times you tossed a coin, without which the number of heads you got makes no sense. But, when you come to think about it, if you already know the mean, this means automatically that you don't need all of the data values in your sample to be able to calculate the standard deviation. Why is this? Well, for example, if you have 3 numbers and you know their mean is 5, if you then find out that the first 2 numbers are 4 and 5, then the last value has to be 6. It cannot vary. So once you know the mean, you only need to know 2 of those numbers, and then you then automatically know the last number, a bit like not needing to turn over the last cup to know where the ball is. So because you already know the mean, the standard deviation doesn't depend on each and every one of the values in your sample. The value of the standard deviation only depends on n-1 of the values. Because you've already worked out the mean, the nth value in your sample effectively doesn't contribute to the standard deviation. Thus, the number of pieces of information that go into calculating the standard deviation, that is, the degrees of freedom, is n-1. This is important especially for small samples. If we worked out the average deviation from the mean, that is, the standard deviation, by dividing by the full sample size, n, we'd basically be including that last redundant data point which cannot contribute to the standard deviation. That would cause us to underestimate the standard deviation. Instead, we divide by only the number of data points that genuinely contributed to the standard deviation. In exactly the same way, we use degrees of freedom when calculating the test statistic when we perform a statistical test. Calculating any test statistic, like a t-statistic or a chi-squared, usually involves having to first calculate in advance a bunch of other numbers, like means, totals, and variances. The more of these you have to calculate in advance, the fewer degrees of freedom there will be. That is, the fewer independent pieces of data from your samples there will be available to make the calculation. For a one-sample t-test, you only have to know the mean of your sample to calculate the t-statistic. So the degrees of freedom is n-1. For a two-sample t-test, you have to know the means of both samples. That is, 2 pieces of information. So the degrees of freedom you have to play with is the combined sample size minus 2. This is really important because the interpretation of your test statistic is different depending on how many degrees of freedom it is based on, and it's meaningless without that context of the degrees of freedom. Specifically, your p-value, remember that is, how unusual your data would be if the null hypothesis were true, depends on both the t-statistic and the degrees of freedom. For example, a chi-squared of 4 is significant, p is really low, 0.046, if it's calculated with 1 degree of freedom, but non-significant, p equals 0.135, if it's calculated with 2 degrees of freedom. So this is a bit like saying my team won 9 matches this year. If we'd played a total of 10 matches in the year, that would be really impressive. But if that number was 9 out of 100 matches, less impressive. Degrees of freedom is a tricky concept, and I don't expect everyone to finish the course understanding it fully. But remember, you won't be assessed on it. This is really just for context and to help you explore.